last year we had to know about the forces between particles and solids. We were told about metallic solids with their particles being cations and a sea of valence electrons and it being the metallic bond. We were told about ionic compounds like sodium chloride, copper sulfate, that sort of thing, being made up of charged ions, cations and anions held together by electrostatic attractions that were called ionic bonds. We were told about macromolecules like diamond, graphite and silica or glass, which were made up of atoms held together by strong covalent bonds in a 3D network, which explained their sort of crystalline structure, their strength and so on. And we were taught about molecules, things like sulfur, S8, things like wax, those sorts of things, which, or even water is a good example, is ice, which, while discrete molecules, were held together by intermolecular forces that we may or may not have had explained to us as being called van der Waals forces or London forces or dispersion forces. This year we need to know a little bit more. We need to know about the metallic bond, the covalent bond and the ionic bond still. We need to know that the covalent bond and the ionic bond sort of are arbitrary terms that we use to describe a bond that is somewhere on our electronegativity difference continuum. They're not really a correct word. You know, if we had a difference of about 1.7, that bond is going to have some covalent properties and some ionic properties. So it's not actually as clear cut as it was last year. But what we also need to look at is this group of intermolecular bonds that maybe need to be explored a bit more. And the other ones I want to look at in a bit more depth today. So we should know a bit about ionic, we should know about covalent, we should know about metallic. Those sorts of substances we should remember from last year. So we're just going to tick those ones off. But what we've also got to understand are things like, for example, why iodine is a solid at room temperature, why bromine is a liquid at room temperature, but why the other halogens are gases. They're all held together by a pure covalent bond because same element, electronegativity difference must be zero. How come they've got different states of matter? That implies that there's different forces acting there. And actually there's not. It's just how strong or how plentiful those forces are. The forces themselves are actually called temporary dipole forces. They're created because in the electron cloud at any one moment, any one instant, the electrons might not be evenly distributed. So I could have a delta minus around, let's say if we're going to go for iodine, around one iodine atom, and a delta plus therefore around at the other side of the molecule, because the electron cloud just for a moment, just for an instant, is centered a little bit more this way than this way. And that's what we call an instantaneous or temporary dipole. If that iodine molecule comes near a neighbouring iodine molecule, it will induce a dipole in that one. This delta minus, being here, will push those electrons this way a little bit, creating a delta minus here and a delta plus here, creating a weak bond between those two electron clouds, a temporary dipole. Because iodine has such a large electron cloud, these dipoles are more likely to occur. Fluorine, on the other hand, has a tiny electron cloud, so these instantaneous dipoles are very unlikely to occur. So fluorine is gas, because for there to be enough bonds, temporary dipoles formed, so enough temporary dipole forces between fluorine molecules, the probability is very, very low. Whereas in iodine with the large electron cloud, I shouldn't really show it like that, but the attraction between these two can be formed more readily. So that and can be more easily induced by a neighbouring molecule, which creates plenty of these forces, which makes iodine a solid. However, these are very, very weak forces, very weak forces. So they're easily overcome. What that means is that when we heat iodine, it doesn't become a liquid unless we do it under pressure. If we heat it, they are overcome so easily that a whole lot of them are overcome at once, and it sublimes. Okay, so that sort of is an explanation more than a justification of some of the physical properties of iodine. Another one that we should know is the permanent dipole, which is our other type of what we've called in previous years van der Waals forces. And that's when you've got something like ammonia or water. I'm not going to use those two though because they're actually examples of things with hydrogen bonds. So let's say instead it's something like chloromethane, where I've got this sort of molecule here. Now there's a permanent dipole within the molecule due to a polar covalent bond that is in this direction, because the chlorine is significantly more electronegative than the carbon. So it means that we've got a delta minus here, and the bottom of this molecule is going to be delta plus. A permanent dipole, a polar molecule. If I have a polar molecule, then every molecule contains a permanent dipole, which means the delta negative side will be attracted to the delta positive of a neighbouring molecule. This is a bit stronger than a temporary dipole. It's only really stronger because they're always there, whereas temporary dipoles come and go, hence the name. But this is also why some polar solvents will eventually dissolve non-polar solutes, because there's going to be enough temporary dipoles here to allow some solubility. So you can actually dissolve iodine in water eventually. It just takes a long time. So your permanent dipole forces are just a bit stronger than your temporary dipole forces. We normally see this in the molecules that have got very similar molar masses or whatever. They've got a considerably higher melting or boiling point. And the last one is a hydrogen bond, which I briefly mentioned before. If hydrogen is bound to a highly electronegative element, and by this we mean fluorine, oxygen, or nitrogen, sorry, not neon. If it's bound to one of those, then it's more than just a dipole being formed. So I'm going to use water because it's our most common one to use. So I've got my highly electronegative oxygen. Now this may not be water, it could be methanol. So this could be a CH3 instead. I like using water though instead, it's easier. When it comes near a neighbouring molecule, then it actually forms a bond that is about 10% the strength of a covalent bond. It's actually quite strong between this hydrogen and this oxygen of the neighbouring one. There's also a permanent dipole force here as well. So we've got two things happening at once. Permanent dipoles are in here, but so are hydrogen bonds, and they are far stronger. This is why, if it wasn't for these, water would be a gas at room temperature. If it was just permanent dipoles at play, water would be a gas at room temperature. The forces would not be strong enough to keep it in the liquid phase. They also have something to do with why water expands when it becomes ice, because these are formed so much and they have a certain length. You know, when we looked at spectroscopy, we could find, you know, like resonant frequencies and so on. Bonds have particular lengths as well. Because of the length of this bond, ice actually takes up more space than water, so therefore floats on top of water. Again, it's because of hydrogen bonding being so strong in a particular length. So if hydrogen is bound to fluorine, nitrogen or oxygen, you can expect hydrogen bonding to be in play. And it's our new one for learning about this year. It's not in one of my two examples here that I've asked you to write about, but it is going to be in an activity I get you to do shortly, which is a graphing activity. Okay, we'll stop that there, please.